We are going to have a second quiz on November the 1st. The second quiz covers whatever from the last quiz until next week. So it looks like we are going to have 2 quiz and 1 final. Or maybe 1 more quiz. It depends on. So the previous result about Cauchy's integral theorem and integral formula says that if Fc has poles at etc., then Fc dz is 2 pi I sum over I residue f zi. This is a really amazing result that even though Cauchy and the mathematicians in 18th century period didn't have a computer, but they were able to do many very complicated form of integration. And that has been particularly true for the mathematicians in Soviet Union until 1980s, because they were lacking behind the computer technology compared with the Western countries. So they were heavy focus on this complex analysis on the very complicated form of integrals. And I think the book by Rizik or table of integrals. It's published in 1980s. They contained about 30,000 integrals. About 2,000 pages thick. So you can probably Google it. Let me check. I think it's Rizik, but Rizik. Scratch time and Rizik. Table of integrals, series, and product. Probably you might be able to get PDF file, 122 pages. The Americans has a bit more moderate book, CRT table. Integral. About 400 pages, maybe a few thousand integrals though. It's amazing that 1959, so anybody know the name of Sputnik? It's the first satellite launched by the Soviet Union in 1959. And there was a rumor that they have done all the calculations, especially integrals for how to calculate trajectories and things like that using the complex analysis by hand, because they didn't have a computer. In 1930s, also, the famous airplanes like Messerschmitt, Me-109, or Japanese Zero Fighter. All those designs also need a lot of complex integrations, and they're all done by hand. That's really amazing. These days, just you can do using computers to design aircraft, other things, rocket, missiles. Until 100 years ago, or maybe 50 years ago, many complicated integration has relied on this complex integration. So even though we have computers and we can do many calculations numerically, but still it does have, if you can get some analytical result by hand. So we are going to do some more complicated integrals, for example. Think about this complex function f of z. The real function doesn't have a pole, right? Because the exponential axis is always greater than 0. in real world, right? How about in complex domain? Exponential z can be -1, right? So if z has a pole, actually poles at z pi I, 3 pi I, 5 pi I, right? Etc., etc., etc. So we can actually choose pi I, 3 pi I. So we can choose the contour in the following way. C1, CR. So let's say C is composed of C1 plus CR. Then on the limit, as R goes to limit, this integral basically it becomes minus infinity to infinite on this real axis, right? So here z is x. On this real axis, z is same as x, right? So this integral becomes oh, sorry. Must be. Oh, I still need to wake me up. Exponential x plus 1 alpha x tx CR is simply 2 pi I residue f pi I residue f 3 pi I, etc., etc. Infinite summation. And this is your integration I, right? So I'll try to go slowly as much as possible so you can understand the progress. You can follow me. So actually this is what we need. And we are going to show that this is going to be 0, right? We will show that this rail goes to 0 as R goes to infinite. But we are going to show this. But so this whole complex integration is the one that we wanted I plus something which is going to be 0. Then, because this whole integration is enclosing this infinite number of poles, so it's going to be summation. So let's do this first, this summation first. So ft exponential z plus 1 alpha z. Alpha is between 0 and 1. So what is the residue? Pi I. It's the same as z equals to pi I, z minus pi I, exponential z plus 1, exponential alpha z, right? So what happens? This becomes or z minus pi I goes to delta, delta goes to 0, delta over exponential pi I plus delta minus right? Because this is same as 0. Exponential pi I is minus 1, right? So you can actually substitute 0. And if it's delta, then it's the derivative of this, right? So it becomes simply e to pi I over 1, right? This is minus 1. Therefore, residue of pi I is actually minus exponential alpha pi I. Or actually, I have shown this another result when fz is nz over dz, then residue of ci is t prime zi and zi. I think I have done this before, right? So using this way, residue of 3 pi I is minus exponential 3 alpha pi I, etc., etc., etc. The summation of this, I will let you copy. Therefore, residue of pi I, residue of 3 pi I, residue of 5 pi I, etc., etc., is minus exponential alpha pi I minus exponential 3 alpha pi I minus exponential 5 alpha pi I, etc. this is minus exponential alpha pi I 1 plus exponential 2 alpha pi I exponential 4 alpha pi I So this is infinite geometrical series. So we can say alpha pi I 1 minus exponential 2 alpha pi I, right? This is infinite geometrical series. 1 r plus r square plus etc. etc. And exponential alpha pi is always less than 1. So it becomes exponential alpha pi I exponential 2 alpha pi I minus 1, same as 1 over exponential alpha pi I minus exponential minus alpha pi I, and this is same as 1 over 2i sine alpha pi, right? So as a result, 2 pi I summation of residue f pi I plus residue f 3 pi I plus residue f 5 pi I, etc., is 2 pi I divided by 2i sine alpha pi. It becomes pi over sine alpha pi. So we also have pi. This is a bit easier integration. Oops. So this is rule C, C1, CR. C1 is minus infinite to infinite, x plus 1, exponential alpha x dx. So we have this one, for integration, C. C is C1 plus CR. C exponential z plus 1 exponential alpha z dz, the same as this is C1 exponential x plus 1 alpha x dx. So C1 is actually minus infinite to infinite plus limit r goes to infinite CR z plus 1 exponential alpha z dz is 2 pi I residue f pi I residue f 3 pi I, etc., etc. This is pi over sine alpha, alpha pi. Right? Now let's show that this goes let's check whether this goes to 0 or not. Let's focus on this integral. I theta dz r exponential I theta I d theta. So this integral CR exponential z plus 1 alpha z dz. The absolute value of this integral is actually 0 to 2 pi less than r exponential I theta plus 1 exponential alpha r I theta I r exponential I theta d theta, right? It's less than pi times exponential r alpha r pi r exponential alpha minus 1 r, right? But since alpha is between 0 and 1, alpha minus 1 is less than 0, right? So as r goes to infinite, this pi r exponential alpha minus r goes to 0, right? This is negative. This is negative, right? The exponential function goes to 0 much faster than r. The whole thing goes to 0, right? So, therefore, as the limit goes to infinite, CR fz dz goes to 0. Therefore, this integration pi over sine alpha pi. This is a bit amazing that, again, we have pi. This integral doesn't involve anything related to circle, right? But nevertheless, the result contains some pi. So it looks like pi is everywhere. Now, this one space-time structure. So I think if there is a God who created this universe, he just pi. It's that signature. This is pi in everywhere. Also in Buddhism, they are talking about that. So this pi. So if you take a close look at the Buddhism, then there is a circle everywhere. That means pi. So it's really interesting that how come those religions contain those pi, which is a signature. of a circle. So pi is between the ratio between the circumference and diameter of a circle in particular geometry. This is really amazing. So, any questions about this particular problem before we move on to next? So I found there about, so far, the tabulate in complex integration is about 30,000. But in this class, I think we can cover maybe less than 5 or 6. So if you're interested, maybe you can take a look at those books I recommended. You don't have to buy. I think they have PDF files around. So you can just download the PDF. And some integrals, you can do it by hand, hopefully. Another integral is a bit interesting. X cubed. This integral is a bit tricky because there is no known formula to do this. So we are going to consider the following example. There is a reason why we consider this rule. Or you can consider FG, so it's okay. But I choose the different alphabet because FG is usually, when we say FG is 1 over z squared plus 1, but it has nothing to do with that. So right, according to the definition of a log function. So this is not single valued, right? So on C1, so we have a branch cut here. On C1, C is x, right? On C2, C is x times exponential I 2 pi. So C1 and C2. C1 is above the x-axis. So this is x-axis. So on C1, which is just above the x-axis, and C1 you can say z is x, right? How about on C2? We have expense 2 pi I, right? Here. So log z is simply log x for x greater than 0. How about here? Log z is log x plus 2 pi I for x greater than 0, right? So on this axis, z is x. So when you take a logarithmic z, which is simply log x. However, on C2, which is below the x-axis, that means you just circle around this, then this is, you have exponential additional argument, right? 2 pi I. Argument or phase, 위상, 2 pi I. So if you take the log, then become log x plus 2 pi I. So C1 GZ GZ is from 0 to infinite x cubed plus 1 log x dx. How about C2? This is C2 is from infinite to 0, right? Direction is from infinite to 0, exponential x, not exponential, x to the 3 plus 1 log x plus 2 pi I, right? Dx. It is, okay. Copy. And actually, I'm kind of getting lazy, so I'm going to copy this whole thing too. Copy. Paste. Paste. Let's move this here. It's nice. So therefore, C1 GZ DZ plus C2 GZ DZ is from 0 to infinite x cubed plus 1 log x dx minus from 0 to infinite, x plus 1 log x plus 2 pi I dx, right? We have minus sign because we change the limit. The C2 is from infinity to 0, but it can be 0 to infinity but with the minus sign, right? So this and this cancels each other. Becomes minus 2 pi I 0 to infinite x cubed plus I dx. And this is what? Our example, right? I. Perhaps you can take a break for a few minutes and then continue. Otherwise, it will take another 20 minutes. So, sorry. There are two things to show. One is the first one, CR integration goes to 0, and 2, 0 integration 0. That we need to show. Now we need to find the location of poles. Right? So what should I do? Maybe I should draw it again. Here. C1 plus C2 is minus 2 pi I times I. C1, CR, C2, 0. This function g to the q plus 1 log z. So we need to find the location of the pole. zq plus 1 is 0, right? So z3 is minus 1, which is the same as exponential pi I plus minus 2n pi I, right? So z can be ci exponential 3 over pi I plus minus 2n pi I. So we have first pole here, C0, C1, C2. So Z0 is exponential pi I over 3. Z1 is n is equal to 1. Cn. Let's say Cn. C1 is exponential 3 over pi I plus 2 pi I is exponential pi I, right? So this is G1. G2 is exponential 3 over pi I plus 4 pi I exponential 3 over 5 pi I. So we have three locations. So C0 exponential I 3 pi, C1 is exponential I pi, C2 is exponential 3 over 5 pi I. So this is Tz over Nz. So we need to find the residue, right? So residue G exponential pi I over 3 is, probably need to have some boundary here. Is residue is Gn d prime Zn and Zn, right? So that is, you differentiate 3 times exponential pi I over 3 square, right? Over pi I over 3. Rho exponential pi I over 3, pi I over 3. So this is 3 times 9 times pi I exponential 2 pi I over 3, or 9 over pi I exponential minus 2 pi I over 3, which is pi I over 9 cosine 2 pi over 3 minus I sine 2 pi over 3. We have 올사 탄코 or sine tan cosine. So cosine 2 pi I over 3 is what? Pi I over 9 cosine 2 pi over 3. cosine 120도 minus 1/2, right? But sine is positive, so minus I root 3 over 2. Now, pi I. I think we have 5 pi over I. So let's make a copy. go back. G1, GG is log C. The residue G pi I is what? 3 times exponential pi I square, right? And log exponential pi I is pi I over 3. 2 pi I, 3 over pi I. Number 3, GI is over 3, right? Residue G 3, 5 pi I over 3 is exponential log exponential 3, 5 pi I, 3 times exponential 3, 5 pi I square is 9 over pi exponential 3 over 10 pi I the same as 4 pi I, right? Pi I. You can put this, right? 2 pi is 1. So this is same as 9 over 5 pi I exponential minus pi I cosine 3 over pi I minus I sine 3 over 4 pi I or sine co. So 3 over 4 pi is here, right? Cosine is plus. Sine is minus, right? So 1/2 plus I let me see, also tanko cosine 4 pi. Cosine 3 4 pi also tanko 4 pi over 3 4 pi over 3 over pi. So let me check. Y가 180도, 180, 240, 90. 이쪽인가? Right. This is minus, right? Sorry, I was confused. And previous one, we need to have a result. This one. Copy this result. Residue G exponential 3, right? That's number 1. Paste. Number 2, residue 3 pi I, right? 3 residue 3 exponential 2 pi I over 3. Oh no, 4 pi. No, 5. So if we add them together, what do we get? Residue G exponential pi I over 3. Residue G exponential pi I plus residue G exponential 5 pi I over 3 is 9 over pi I minus 1/2 minus I is equal to 2 plus 3 is more, same as 3 pi I, right? Plus 9 over 5 pi I minus 1/2 plus I equal to 3. Combine over 9 minus 1/2 plus 3 minus 2 over 5, right? Minus I 2 over root 2 3 plus 2 over 5 I root 2 3, right? Oh. This cancels each other, right? So it becomes pi I over 9, 2 over 5 I root 2 3 minus 1 I root 2 3 is 9 pi I 2 over 4 I root 2 3 is minus 9 over 2 root 3 pi. So anybody remembers the C1 plus C2? C1 plus C2 was, therefore, minus 2 pi I is 2 pi I times minus 9 over 2 root 3 pi. So this cancels each other. I think of course here we need to have 0 plus CR, right? But they are going to be 0. So we know the answer roughly that I is 9 over 2 root 3 pi. Pi I, 2 pi I, minus, right? I. So residue is this, minus 2, 4, root 3, pi I. So we still need to show that the other two integrals goes to 0, but roughly this minus 2 root 3, right? This is our branch. You have 3 poles, right? In this case. So this integral, closed integral over C is C1, C2, CR plus 0, C to the cube plus 1, log Z dZ, C1, Z dZ, C2, log Z dZ, CR, R goes to infinite, Z to the cube plus 1, log Z dZ, plus log goes to 0, 0, Z dZ. We already have this, right? If we add them together, what do we have? Minus 2 pi I, this integral, I, plus, we have CR plus 0 is 2 pi I, residue G C0, residue G C1, residue G C2. we know that 2 pi I times this is minus 9 over 2 square root 3 pi, right? We already have this. Let me just check the number. So we need to show these two vanishes. So can I move on, or is it time to copy? We itemized all the different parts, and all you need to show that the other two integrals just goes to 0. Right? The first things first, this part. So on CR, G is R to the exponential I theta, theta. So dz R exponential I theta, I d theta, right? Absolute value of CR log Z dz is less than 0 to 2 pi d to the q R to this 1 R plus I theta R d theta, right? If you take the absolute value, log Z is log R plus I theta. Less than 1 over R square you can put this log. Is less than R to the square log R 2 pi I 1 plus log R square theta square d theta. But this factor is dominated by this, right? and you can say this goes to 0. When I goes to infinite, log r also goes to infinite, right? So this term goes to 0. This term, because basically this term goes to 2 pi, but I square is going much faster than log, so still goes to 0. Right? This goes to 0. This term goes to 2 pi. As I goes to infinite, as I goes to infinite, this term becomes 0. So this whole integration becomes 2 pi. But the common factor goes to 0. So as a result, CR integration is going to 0. Now the other integral, this integral, the rho exponential I theta, dz is rho exponential I theta, I d theta. So it becomes 2 pi to 0 rho exponential I theta to the cube plus 1 log rho plus I theta rho exponential I theta I d theta become rho times 2 pi 0 rho exponential I theta to the cube plus 1 log rho plus I theta I d theta. Because the common factor is rho, it goes to 0 as rho goes to 0, right? Therefore, so we have both integral is going to 0. We have shown that. Therefore, to this integral c t to the cube plus 1 log z dz is basically 2 pi I from minus infinity to infinite x to the 1 dx, right? This is our integral. I is 2 pi I times minus 9 over 2 root square root of 3 pi. So this cancels this and this. So we have minus infinity to infinite x cubed plus 1 dx 9 over 2 square root of 3 pi. Again, you have pi. This integral has nothing to do with circle, right? But if you do that, you seem to have pi. So somebody or something has left the signature. Again, right? Pi. The next integral is a little bit more complicated, but more exciting. So any questions about this integral? Somehow today seems to be the attendance rate is low, so maybe I'm surprised with it. Why don't you lock the door? Do you mean that? Is. I announced in the beginning of the class, right? It's going to be 5 points. Maybe 10 points. Number 1. Write your name. Just pick a piece of paper. 종이 한 장 꺼내가지고 your name, serial number, student number, write your name. Number 2, write my name. Or your professor name. It's going to be 10 points. And there is no excuse whatsoever who did not come to this class today. So only you can get 10 points. One minute will be enough. Right? Your name and my name. But don't forget to put your name and your serial number, 학번, and two questions, 1, 2. So that's going to be 5 points each. So the price is more like a piece of the sale. And if you're not here, then you just missed the chance. Okay, I think somebody can collect the answer sheet, right? 가방이 보고 있어? Okay, so let's continue. Another example, which is actually very complicated. So far, all the integrations were involved from either minus infinity to infinity or 0 to infinity. But this integral is minus 1 to 1. And 0 to 1 minus x squared or something like that. So we also need to have c squared minus 1 to the half 1 plus c squared. Consider this. Consider this function. Square root of z plus 1 half. Which is what? Square root of r1 exponential I theta 1 over 2 square root of r2 exponential I theta 2 over 2, right? So this is square root of r1 r2 exponential I theta 1 plus theta 2 over 2. So let's consider 6.1, 2, 3, 4, 5, 6. And angle. One, 2, 3, 4, 5, 6. Here, so what we assume that 1, 2, 3, 4, 5, 6 are all very close to x-axis. So this is your x-axis. Let's consider point 1. If you look at x-axis, what is angle theta 1? Theta 1 is from here to here angle. Theta 1 is 0, right? Because this point is located on the x-axis. So the angle measured from here, this point, you can be A1 or -1, but also you can put A or B, or sometimes B. So theta 1, at this point, theta 1 is 0, right? How about theta 2? 0. Theta 1 is 0. Theta 2 is equal to 0. How about this point? Point 2. Theta 1 is still 0, right? How about theta 2? At this point, you measure this one. Pi. So, theta 1 is 0. Theta 2 is pi. How about this point, 3 point? Theta 1, pi. Theta 2, pi. Theta 1 is pi. Theta 2 is pi. How about this below 0? Theta 1, still pi, right? Theta 2, still pi. Here is tricky. Theta 1 is still pi, right? No, theta 2 is pi. How about theta 2? Theta 2, 2 pi. So theta 1, 2 pi. Theta 2 is pi. How about point 6? Theta 2 is 2 pi. Theta 1 is 2 pi. Pi, theta 2 is 2 pi. Oh. So I'm going to put this table to the next page. Copy and paste. I think we need also this picture. Copy, paste, paste. So let's move this. Paste. Now, how about this half angle? Because one half is R1, R2 exponential I theta 1 plus theta 2, right? So now we can calculate the table. One, 2, 3, 4, 5, 6. Now let's calculate 1 over 2 theta 1 plus theta 2. At this point, both are 0, right? So they are again 0, right? Here, theta 1 is pi, theta 2 is, no, theta 1 is 0 at this point. Theta 1 is 0, theta 2 is pi, so 1/2 is pi over 2. How about 3? At this point, pi, right? How about 4? 4 is again pi. How about 5.5? 3 pi over 2, right? Here, 2 pi. Okay. So if you cross x-axis from 1 to 6, from 0 to 2 pi, it's the same, right? How about 3 to 4? If you cross this axis, again pi to pi, same. However, if you cross this 2 to 5, there is a phase change. So this function is in a single value along this line. So we should put the branch where? From -1 to 1. So this is branch. We need to cut branch. Because it's not single valued. When we cross the x-axis at 2 to 5. So when you cross x-axis from 2 to 5, there's a phase change. So we need to prevent the crossing by putting the branch. So we again we need this. Now we can do the integration. So we have G. Oh, sorry. What am I doing? This. We have this integration. Of course, this is CR. Okay. C1.
is C2, 0, C3, C4, CR. So this is our point. This is point 1, point 2, point 3, point 4. Oh, maybe I should use different color to denote the points. This is our point 1, point 2, point 3, point 4, point 5, C1, C2, C3, C4, and this is 6. And we have 2 poles right here. High I, no, I, minus I. And GC can be written as this following way. Right? Let me see. Too small, right? I'll write it big. Big way. This function can be written this following way. Absolute value of c squared minus 1, right? And exponential theta 1 plus theta 2 times c squared plus 1. I think I need to make a copy again. Whole thing. Which direction? C1, C4, right? Just for your convenience, just this table. C2 and C3, right? So let's do this. Let's do this first. This is -1, this is 1. C1, C4. Here, 1/2 theta 1 plus theta 2 is pi, right? And the same, this is 0.3, this is 0.4. Here also 1/2 theta 1 plus theta 2 is pi, right? Maybe I should keep this table. Here. Right. So this is your function, GZ. GZ C square minus 1 to the half. C square plus 1 over 1, right? So on C1, GZ can be written as the following, right? Can be written as square root of x square minus 1 exponential pi I, right? On C1, C3, no. On both 3 and 4, right? Maybe I can write in red color. 3 and 4. Here, absolute value of z square minus 1, 1/2.
On this side, here, 3 and 4, this angle is pi, right? So this function can be written as absolute value of this with the phase, which is exponential pi, right? And the absolute value of this can be written as x squared minus 1. So on C1, GZ can be written as
Square root of x square minus 1 exponential I pi I x square 1, right? How about on C2, C4? GZ same, right? Square root of x square minus 1 exponential I pi x square plus 1. Because
if you cross from here to here, the phase does not change. Still remain the same, pi, right?
so what happens if you add this integral together? It's C1 GZ plus C2 C4 GZ DZ is C1 is minus infinity to minus 1 square root of x square plus 1 exponential pi I is minus 1 x square plus 1 dx plus C4 is from minus 1 to infinite, minus infinite, right? Again, the same. Square root of x squared plus 1 minus 1 x squared plus 1 dx, which is 0. Great, right? Which is from minus 1.
So C1 and C4, if we add them together, 0. Now this and this.
We still need to make a copy of this. Copy. Okay. Paste. Here. And another integration. We now need this integration, minus 1 to 1. We continue this integration. We have a branch cut here. I forgot the number. Let's check. This is C2, C3, and this is 0.2, 0.5. We have to be really careful about this. Z squared minus 1 to the half is on 2 which is absolute value of this exponential theta 1 plus theta 2, right? Here, you can say it this way, exponential I pi over 2.
If you take the absolute value of this, whatever, then you can put minus 1 as well. Between minus 1 to 1. So it has to be real value. So we can put this way. But this on 2, the phase is pi over 2. Right? So this is basically I times
How about 5? Root 1 minus x squared exponential I 3 pi over 2, which is minus I squared.
this is interesting, right? Because on this C3, we have the phase is different. So instead of I, it would be minus I.
So this is very interesting. C2, C3, C2 is from minus 1 to 1, square root of I 1 minus x squared 1 plus x squared dx plus C3 is 1, 2 minus 1, right? Direction is opposite. This integral is opposite, right? From 1 to minus 1. But also we have minus I dx. So this minus will actually change the upper limit and lower limit. So it becomes I over 2 2 over I. And you can guess that the other two integrals will go to 0, right? And we have two poles. Because it may take another 20 minutes to finish. Maybe we can stop here today and then continue next week. What do you think? So actually we have done most of the stuff today, but I think for your own benefit, it may be good for you to review something